Hey guys, my name is Noah Jacobson, and today we are going to be doing the Calc BC FRQ from 2011 number 3, and it's on arc length and volume and related rates a little bit. Alright, so you have a function f of x, which is e to the 2x. I know it's a bit small, but it'll be rewritten bigger on a different page. R is the region in the first quadrant bounded by these two lines, the graph of f and the x-axis. The vertical line occurs at x equals k, and the function, since the function is e to the 2x, becomes e to the 2k at point k. Our first part is going to be to write and not evaluate an expression involving an integral that gives us the perimeter of r in terms of k. So to get the perimeter, we're going to need to add up the lengths of all of the sides. So there's 1, 2, 3, 4 sides here, as you can see. We're going to want to find each of them. So these three on the bottom are fairly easy to find the perimeter of. You just kind of need to look at it as a line segment, say how long is this line segment, and then write it down. So this has a height of 1, goes from 0 to 1, so we can just write 1 there. This goes from 0 to k, okay, and it's 0 because it's at the origin. This goes from 0, it's on the x-axis, to e to the 2k. It might trip you up a little bit to go from like 0 to k, but you got to remember you're plugging into, you're looking at the y-coordinate, how the y-coordinate changes since the x-coordinate is constant. So this is going to be e to the 2k. And these are the lengths of these lines. Now, this line right here is going to be a bit harder. This line, since it's a curve, we're going to have to use the arc length formula to find it. And it's just the arc length formula for normal functions, so not for polar or anything weird like that. All right, so I'm going to switch over to the next page. All right, so I just rewrote our functions here. You have f of x is e to the 2x, and then the derivative of that is 2e to the 2x. To find the perimeter, you're going to want to add up all the sides. So you have your side that's 1 plus k plus e to the 2k plus whatever this is. Now to find this arc length, we're going to need the arc length formula. That's going to be, if you remember, the integral from alpha to beta of the square root of 1 plus the derivative of the function squared, as we showed here. Except I'm just putting it from 0 to k instead of a to b. Because as you can see here, we're integrating in the x direction. We're doing, it's dx at the end. So we're going to be wanting, our endpoints are going to want to be our x values, not our y values. All right, so from there you can just plug in f prime and get this. Fortunately, we don't have to solve that integral. I don't know if we could, but whatever, we are fortunate. The next part is a rotation problem. You have to rotate the volume around the x-axis and find the volume of the solid in terms of k. And this one we do have to evaluate the integral, so too bad. This pathetic symbol is a v. What I'm saying is the volume of any rotated object is going to be pi times the integral from alpha to beta of the radius of the solid squared with respect to whatever axis. In this case, we're going to use the x-axis because it's rotated around the x-axis, and it's easier. So yeah, so you have your original graph here. This is r. And you're just, it's as if you're flipping it around. So we know our radius is always going to be r of this. If you can imagine this circle being in here, this is r, and then r turns into this, etc. It might be a bit confusing because I've used the same symbol for area as I did for radius. So I'm sorry about that. Blame the AP test makers. So we can sub in alpha to beta. We can sub in with 0 to k because we're going from x equals 0 to x equals k. It's pi times that, and then r squared. R is going to be f of x because that's the height of this is dependent on f of x because we're just comparing it to the x-axis. So f of x is e to the 2x, so it's going to become e to the 4x when it's squared. Taking the integral of that, we know the integral of e to the 4x will be e to the 4x divided by 4. So I'm just putting this 1/4 out here. Now you have your integral, you're subbing in k, you're subbing in 0. And you get pi e to the 4k divided by 4 minus pi over 4 as your answer. All right, so then we are on to the last problem. The volume V found in part B changes as k changes. If dk dt is 1/3, determine dv dt when k equals 1/2. So we have our variables here. I'll put them in a box. It's easier to read. K prime equals 1/3 and k equals 1/2. To find the rate of volume change, we're going to need to use the fundamental theorem of calculus. So we know the volume is going to be represented by this equation. We showed that in part B. Then to find the rate of volume change, we would just take the derivative of this. Pi isn't going to change because it's a coefficient, but this integral is going to turn into a derivative. And this is just by the fundamental theorem of calculus. So it would become e to the 4k, but we also have to remember the chain rule where we have to take k prime in addition to just, substituting in k. I guess I can go into a bit more detail on this. So if this is, we can just say that's g of x right now, e to the 4x. So when we integrate it, it would have become g to the x, or sorry, g to the k minus g to the 0. And then taking the derivative of that would have, what is it, dx over dt? Taking the derivative of that would cancel out this because it would be a constant, and leave only this because k is a variable. And also you'd have to put k prime on the outside too. So there's your fundamental theorem of calculus proof. So we get through this derivative that dv over dt is k prime times pi times e to the 4k. We can sub in for that and get dv dt is pi e squared over 3. Great. So now it's time for example problems. 2008 number 4 is a really good problem if you want kind of all the stuff discussed in this problem all in one problem. There were a lot of things in this problem. You had arc length, volume, and rotation, and that's all in 2008 too, so it's very much good as almost a replica. 2007 is arc length and rotation, and I like it because it's a bit less straightforward. It's a bit harder of an integral to do, and not just flat out integrate with respect to the x-axis. You have to do more of that subtraction stuff from AB. Then 2016 number 5 was also just really good like this. Combined rotation and related rates. Remember, it was that funnel problem where you had, the funnel that was decreasing in height. Oh, that was a bad drawing. Where you have to rotate it and do related rates and all that. All right, thanks for watching.